Hello students, in this video we will be discussing some problems on elementary properties of a group, right? So first problem is, let G be a group such that A square is equal to E, okay, for all A belonging to G, right? Then show that G is group G is abelian. Okay, so see here, if I'm saying this, A square is equal to identity for all A belonging to G, okay, then it means order of A is equal to 2 for all A belonging to G, or we can say every element of G except identity element has order 2. Okay, so this question can be also asked in alternate form. Show that, or if, okay, if every element of a group, every element of a group except identity element, okay, except identity element is of order 2, then show that group is abelian, okay. So here as you can see, order of every element except identity element is 2. It means A square is equal to 2 for all the elements of G. It means if I multiply it both the side by inverse of the 2, inverse of the A, we get A to A inverse is equal to E time A inverse. So it is equal to A, right? And right hand side it would be equal to A inverse. So it means A is equal to A inverse. So from this thing comes the alternate form of this question. Okay, alternatively this can be also asked in this way. Show that a group, okay, what does it imply? If order of a group, okay, sorry, if order of every element of a group, okay, if order of every element of a group, okay, is 2, then it is inverse of itself. Okay, then it is inverse of itself, that is A is inverse of itself, because A inverse is equal to A and A is equal to A inverse. It means A is inverse of itself when it is possible, when order of A is 2, or we can say if order of every element is 2, then every element is inverse of itself. Okay, so we can this question can be asked in this way. Show that a group in which every element is its own inverse, show that a group in which every element is its own inverse is abelian group. Okay, is abelian group. Now solution. Let G be a group let G be a group and A comma B belongs to G. Okay, so in this group order of every element is 2, right? So A square is equal to E and B square would be also equal to E. Also you see, if A and B belongs to G, then AB also belongs to G. Okay, and we know order of every element in this group is 2, therefore AB square is also equal to E. Okay, from here if you multiply by this, implies A into A or A square into A inverse is equal to E time A inverse. Okay, this implies A is equal to A inverse. Okay, similarly B is equal to B inverse and AB is equal to AB inverse. Okay, we know AB inverse is equal to B inverse A inverse by reversal law. Now we want to prove that this group is abelian. For that we need to show that AB is equal to BA. Okay, so see, AB is equal to, can be written A is equal to AB is equal to A inverse B inverse. Why? Because A is equal to A inverse and B is equal to B inverse. Okay, so again using the reversal law, A B what if it would be better to start with BA. Okay, so we can use the given proved information. So BA is equal to B inverse A inverse, which could be written equal to, by reversal law, AB inverse, and AB inverse is equal to AB, right? So therefore BA is equal to AB, or we can write AB is equal to BA. Thus for all A, because we have taken A and B arbitrarily, so thus G is abelian. Okay, one more problem. If in a group G A5 is equal to E and AB A inverse is equal to B square for all A comma B belonging to G, then prove that if B is equal to not equal to identity, okay, then prove that you just write, then prove that order of B is equal to 31. Okay, B is not equal to identity. Okay, so we need to prove this. So prove or solution. See here, what is B? B order of A is equal to 5, that is A power 5 is equal to E, and also we are given that B square is equal to AB A inverse. If we multiply B by B square by B square, we get, okay, squaring above these above equation, we get B4 is equal to AB A inverse square, right? Using third result, I think third result of theorem 4, we get a b square a inverse. So again, since you see b square is equal to ab a inverse into a, so it is equal to कितना हो जाएगा ये a square b and this is inverse, okay, and a minus 2, right? So this is b4. Again squaring, we get b8 is equal to a square b square a minus 2 whole square, okay, which is equal to, using the same, invoking the same theorem again, it we used, okay, here we are going to write it b4 minus 2, okay, third part 3 of theorem 4, okay, what we did in the last video. So I'm sorry, this was not b square, it was b only, okay, b, because we have replaced b square by ab minus ab a inverse, okay. So this is, so this would be b square, okay, again replacing b square by this thing, okay, we get a square a b a inverse a minus 2, okay, which is equal to a cube b a minus 3. Again squaring, this is 16, okay, and we get a cube b a minus 3 whole square, which is equal to a cube b square a cube, okay. In place of b square we can write a cube a b a inverse a cube, which is equal to a4 b a minus 4. Now squaring one more time, this is 32 now, a4 b a minus 4 whole power 2, which is equal to a4 b square a minus 4, replacing b square by a b a inverse a minus 4, which is a5 b a minus 5, right? So this is equal to 32. Since order of a is equal to 5, this implies a5 is equal to identity. Also a minus 5 would be, because we know order of a is equal to order of a inverse, so order of, okay, a inverse would be also 5, so therefore this is equal to identity. So this thing is identity b, and this is also identity, so it is equal to b. So b32 is equal to b. This implies, taking it to the another side, we get 32 into b inverse is equal to identity, okay. This implies b31 is equal to identity, which implies order of b divides 31, okay. But we know this is a prime number, right? So it can be only divided by 1 or itself. So if it is divided, if order, okay, if it is being divided by 1, it means order of b is equal to 1. But we know there is only one element in a group which used to have order equal to 1, and that element is identity. But initially we are given that b is not equal to identity, therefore it must be 31 who is dividing this thing 31, okay. So this implies order of b is equal to 31, okay. So thus we have found out the order of b, okay.